We want to use Green's theorem to evaluate the line integral along the curve C of f dot differential r, where the vector field f is defined here, and the curve C consists of the arc of the curve y equals 3x minus x squared from 0, 0 to 3, 0, and the line segment from 3, 0 to 0, 0. And we're given a hint here to check the orientation of the curve before applying Green's theorem. So again, the curve C consists of the arc. So the curve C consists of the curve along y equals 3 minus x squared graphed here from 0, 0 to 3, 0, so along here, and then from this point, 3, 0, back along the line segment to 0, 0. So notice how the orientation is indicated by these arrows, but this orientation is not the orientation indicated by Green's theorem. For a quick review, Green's theorem states that the curve C must be a simply connected piecewise smooth curve with a positive or counterclockwise orientation that encloses a region R. So if the curve C has a positive orientation, that means the region R would always be on the left side of the curve. So going back to our example, notice how we don't have a positive or counterclockwise orientation, we have a clockwise or a negative orientation. Notice how in this direction the curve is always on the right, not on the left, which means to apply Green's theorem, we'll have to use the opposite orientation, and therefore we're going to have the line integral along the opposite of curve C of f dot differential r. And now applying a property of integrals shown here, the line integral along the opposite of curve C of f dot differential r equals the opposite of the line integral along the curve C of f dot differential r. So this is equal to the opposite of the integral along the curve C of f dot differential r. So now we can apply Green's theorem in this form here, where P is going to be the x component of the vector field f. So P is equal to, let's write this as x to the 1/2 plus 5y, and Q is equal to the y component, which is 4x, plus, let's write this as y to the 1/2. And now we need to find the partial of Q with respect to x and the partial of P with respect to y. So the partial of Q with respect to x is equal to the derivative of 4x plus y to the 1/2 with respect to x, which would be 4. And now we need to find the partial of P with respect to y, which is equal to the derivative of x to the 1/2 plus 5y with respect to y, which is 5. So now applying Green's theorem, we're going to have the opposite of the double integral over the region R of the partial of Q with respect to x, which is 4, minus the partial of P with respect to y, which is 5. Now differential A is equal to dy dx or dx dy, looking at the region R, because it's bounded above by this parabola. Let's integrate first with respect to y, and then with respect to x. So we'll have dy dx. And now let's determine the limits of integration for y. Again, the region is bounded below by y equals 0, and above by the curve y equals 3x minus x squared. So limits of integration for y are going to be from 0 to 3x minus x squared, and then with respect to x, we'll integrate from 0 to 3. Let's simplify and then evaluate this on the next slide. We'll notice how we have a negative sign here, and this simplifies to -1, so this will simplify to +1. So the double integral of 1 dy dx. So we first integrate with respect to y, so the antiderivative is just y. So big F of b minus big F of a is just going to be the quantity 3x minus x squared minus 0. Integrating with respect to x, we're going to have 3 times x squared divided by 2, or 3/2 x squared, minus x to the third divided by 3, or 1/3 x cubed. And big F of B minus big F of A is going to be 3 halves times 3 squared minus 1/3 times 3 cubed minus, we just have 0 minus 0 and x is 0. So here we'll have 27 halves minus 27 thirds, which is 9, which is equal to 9 halves, or 4.5. I hope you found this helpful.